And we'll start with a quote from Kobe Bryant, a very famous basketball player, who said, "If you want to be a better player, you have to prepare, and prepare some more." And this is true. You can't expect to go and perform someplace without having practiced. You wouldn't be a very good musician, yeah, I can say words, if you just showed up and randomly played an instrument on stage that you'd never tried before. You have to practice. The same is true with math, any subject that you're studying. If you want to do well when your grade is on the line, say an exam, quiz, assignment, whatever, you have to put in the work. You have to put in the practice. So commit. We want you to succeed. You have the ability to succeed. So do what you can to help yourself out. Now, what's our goals for today? We're going to talk about empirical probability and what that means. And then we're going to talk about the idea of union, intersection, and complements of events. And there's already a little spoiler warning. It works like sets. So union is saying either this event or that event happened. Okay, take the union of the possible outcomes, add up those probabilities, and so forth and so on. Now, one thing I did not talk about last time, but I probably should mention, because it's a language that the book uses. There's this notion of simple event versus a compound event. And I didn't explicitly say what these things are. And in case you're encountering some language and it says this is a simple event, it's just a compound event. A simple event just means that there's just a single desirable outcome. There's just one outcome. So remember, when we're talking about our experiments, our random experiments, we have our sample space, which is the set of all possible outcomes. And a simple event says there's only one outcome that's desirable. So that's a simple event. What's a compound event? A compound event is any number of things can happen. So simple is just one, compound is multiple. But technically speaking, compound just says any number. So even a simple event could be argued to be a compound event. All right, so in case you need that language as you're studying. Now, let's do a problem. So we were going to do this last time, but we were short on time. That's okay. That's why we always keep coming back, so we get more time. So suppose you roll 2 dice. Now, when I talk about dice, I'm not going to be fancy. I'm not going to be one of those Dungeons and Dragons people. It's like, oh, is it 12-sided? Is it 10-sided? Is it 100-sided? No. I'm going to assume these are 6-sided dice. 6-sided dice. And what is the probability that the sum of the numbers is 4? So to be clear, when we talk about 6-sided dice, the numbers on the sides are 1, 2, 3, 4, 5, 6. We're also going to assume that these are fair dice, which means that each number is equally likely. Okay, so we want to find what's the probability that the sum of the numbers is 4, and there's another question, what's the probability that the sum of the numbers is 7? Well, what can we think about here? Let's build up our sample space. Or in other words, all possible events. How can we think of it? Well, we have 2 dice. So what we can think of is we can think of an event, or a roll, really consists of a pair of numbers. What's on dice 1 and what's on dice 2. And when I say 2 numbers, I really want to say there's a first dice and there's a second dice. So I want to Sometimes we talk about lists, and sometimes we talk about sets. Lists are order matters, or another way to say it, you can distinguish it. You say, oh, there's multiple coins, I distinguish the coins. There's multiple dice, I distinguish the dice. Sets are, I don't really know which one is which. So, the dice one, how many outcomes are possible for the first dice? There's 6, right? 1, 2, up to 6. How many outcomes are possible for the second dice? Or second die, I know, I'm sorry, I should use the language. Also 6. So, before we write them all down, what's the total number of possible outcomes? 36. Yeah, so this is a case of multiplication. Oh, we'll be here for a few minutes. That's right, about 45 or so. So let's see if we can set up a grid. And I can already tell that some of these cells are going to be hard for me to write the numbers in, but that's okay. So we'll have, say, dice 1 on the horizontal, the rows, dice 2 is the columns. So we again have our possibilities, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And we can just list them all down. So we get 1, 1, 1, 2, 1, 3. And of course, after a while, you realize there's probably better ways to do this. There probably are. But, it's one of those things where you do it once in life, and then you realize, okay, I'll figure out a better way to do things. It's oftentimes how I approach problems. I say, look, if I just have one problem, I'll just do it once. But if I have to do it twice, the second time, I'll write a program. And of course, having to go through and do it by hand the first time really helps you figure out what's going on. And all right, so I'm listing all the possible pairs, almost there. So there we go, all 36 possible outcomes. Okay, so now there's a question. What is the probability that the sum of the numbers is 4? Well, what are we looking for? Yeah, we're looking for pairs where things add up to 4. So can anybody see a pair that adds up to 4? 1 and 3 does it. Anything else? 2 and 2? 3 and 1. And that's it. Okay, so the number of times that we get the desired outcome is 3. The total number of outcomes? 36. Yeah, so we put that together. We say, okay, so it's the number of desired outcomes over the total number of possible outcomes, 3 over 36, or a 1 out of 12 chance. Okay. What's the probability that the sum of the numbers is 7? So now what are we looking for? Pairs that add up to 7 is great. Do you see any? 6 and 1. Any others? Someone said, they made a motion to indicate, go on the diagonal. Yes, it's the diagonal. So the diagonals are the ones with the constant sums. So there are 6 possible ways to add up to 7. All right. So what's the probability that the sum of the numbers is 7? Well, there's 6 possible ways to do it, 36 possible. So 1 out of 6. So in particular, the sum of the dice is not the same. It's not like equally likely to be a 4 as it is to be a 6. It's more likely to be 6. Now, what are the possible sums? The lowest possible sum is 2, and the highest possible sum is 12. What's going to be the most likely sum? The sum with the highest probability? 7, because that's the diagonal that hits the most. And with this, you can answer lots of other questions that are similar. We can say, let's try this question. What is the probability that at least one of the die has a 5 or a 6? So in other words, what's the probability that one of the two is a high roller? And that's not necessarily good depending upon the game, but one of them is a 5 or a 6. Well, what do? You go through and look for everything that has a 5 or a 6 in it. And there's the first die has 5 or 6, and there's the second die has 5 or 6. So it's this sort of upper corner, if you want. So if you start counting, well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So that probability becomes 20 over 36. And you can simplify that. They're both divisible by 4, so that becomes 5 over 9. So you have a better than 50% chance that one of the two dice has a 5 or a 6. Even though individually, it's a relatively smaller chance. It's a 1 out of 3. All right. So these are questions that often get asked. I will say a lot of questions about probability come back to questions about rolling die or flipping coins. So don't be surprised if you encounter such questions. So now I want to turn to what's known as empirical probability. So oftentimes we say, well, let's start with something where we know the odds of the outcomes. So we say, okay, we start with a coin and we'll flip it and we'll say it's 50-50. But what if we don't do that? What if we do something a little different? We say, look, I don't know what the outcomes will be. Can I figure out the probability? So in other words, I have an experiment I'll run, but I don't know what the probabilities are necessarily. What can I do? Well, what I can do is I can use the experiment to estimate the probability. And so when we're talking about these empirical probabilities, what we're talking about, well, it's the probabilities that are based off of our experiments. So, how does that work? Well, we say, look, run the experiment many, many times. And then you say, how often did you get a particular outcome? So, that's the frequency, or the number of times that our outcome occurs. And we say, well, the probability of that outcome is the number of times that we got that outcome over how many experiments we ran. So that's the way we can estimate a particular probability. All right. Now, I will say people have done this before. So I had a person who I've worked with in the past. His name is Percy. I mentioned him when I talked about card shuffling, I think. And one of the things he looked at is he said, well, let's flip a coin. Is flipping a coin, are the odds 50-50? Well, of course, we often say that. But how would you test it? So now, instead of assuming it's 50-50, you say, I want to figure out if it's 50-50. So that's where it's sort of this empirical probability. It's this probability based on experimentation. So how could you test it? Well, here's what he did. He said, I'll get a coin. Now, unfortunately, I don't seem to have a coin with me. That's the unfortunate version of what happens when we go with a cashless society. It's not as exciting to flip cards, but what he did was he built a machine. And the machine flipped the coin 10,000 times. Now you might say, why 10,000? Well, he wanted to make sure there were enough coin flips to get data. And what do you think was the discovery? Was the coin 50-50? Turns out the answer is no. There's actually a very small bias. And you might say, how? Well, when you flip a coin, what can happen is it can give the impression of flipping, but actually not turn over. So, in other words, sometimes you flip a coin, it can wobble without actually turning over. There was an overtime NFL game many years ago where they were broadcasting it on TV, and they started with a coin flip to determine who gets the ball first. And at that time, it was very important who got the ball first. It likely determined the winner. And the referee flipped the coin, and the coin did this. It just traveled straight through the air and landed on the ground. And then the players were like, you got to flip that again. And he did. But it can happen. And so because of that phenomenon, you can see that there's a slight bias. Okay, so the punchline here is if you want to figure out a probability, run the experiment many times. Okay, so there's a question here. You flip a coin 50 times and it comes up head 45 times and tails 5 times. Is it possible that it is a fair coin? Fair meaning 50-50 chance. So can you have a fair coin where it comes up heads 45 times and tails 5 times? Yes or no? The answer is yes, but super unlikely. It's one of those things where the possibility that it was so heavily biased to heads that it would come up, the possibility that's a 50-50, but you got 45 heads and 5 tails, is astronomically small. Ridiculously small. But it's not zero. That's one of the things that's very annoying. You can say, hey, is it possible? Yes. Is it likely? No. And so you have to be careful. Okay, but definitely we say, hey, it's super unlikely, so we say we believe the coin is not fair. All right, that's a reasonable assumption. So given that we think the coin is not fair, what is the probability of it coming up heads and coming up tails? Well, that here, we're using the empirical probability, the probability that follows from experimentation. We have an experiment. We ran an experiment 50 times. This was our experiment. So we say, okay, let's use that. What's the probability that it came up as heads? Based on our experimentation, well, the n, 50 times, and how many times did we get heads? 45. So it looks like the probability of getting a head is 9/10, or 0.9, or if you're talking to your engineer friends, you add a couple zeros and like, whoa, that's way more precise. Engineers like having 4 digits of precision. I don't know what it is, but they love it. Probability of tails? What would that be? Yeah, 5 out of 50, which is 1/10, or 0.1. All right, so that's the idea. Okay. Now, the other thing we want to talk about today is the ideas of intersections, unions, complements, but these are going to follow in line with the same things we've talked about before. So if we have 2 events, the probability of the intersection of the event what does that mean? We want to say, what happens, what's the likelihood that event E and event F both happen? So what do? You intersect their spaces. And you compute their probabilities. It's the same idea as before. And the same works for unions. Now, the nice thing about unions, once we understand intersection, one of the things we said is that if you just look at the size of a union, it's the size of the first set plus the size of the second set minus the size of the intersection. So the probability of two events happening, one of the two happening, take the probability of the first event, add the probability of the second event, subtract the probability of both events. Okay. And the last thing is the probability of the complement, or if you like, not E happening. Well, one of the things that we basically say is something has to happen. So either E, this event E, happens, you get ahead. Or you have not E happening. You don't get ahead. So what that means is if I sum up the probability of an event plus the probability of the complement of the event, they have to add up to 1. Something has to happen. Or the probability of the complement of E is 1 minus the probability of E. Okay. So let's go back to an example. 2 fair die are rolled. What is the probability that the sum is at most 8 and the values of the two differ by at most 1? Okay. Now, this and, which setting are we in? The intersection, the union, or the complement? Intersection. Now, instead of rewriting the whole sample space again, we can just say, well, let's just sort of see what are we going for. So what are the cases we have? We want to have that the sum is at most 8. So where will that be? Sum at most 8. We'll say we want to be down, or I should say, in this portion here. That's where the sum is at most 8. Down here, the sum is 9, 10, 11, or 12. The value of the two differ by at most 1. So that says you look at the die, if they're the same, great. If one is a 3, one is a 4, great. But what if one is a 2 and one is a 4? Then the difference is too big. It's 2. So where are we looking for when we want the difference to be very small? We're looking here. These are the places where the numbers are close together. So, oh my goodness, I'm running out of colors. If we want the numbers to be at most 1 apart, that would be this stretch here. Okay? This piece essentially along roughly the diagonal. So we take the intersection and we get a bunch of data. So let's just write down the pairs that work. So what are the outcomes that work? 1, 1, 1, 2, 2, 1, 2, 2, 2, 3, 3, 2, 3, 3, 3, 4, 4, 3, and 4, 4, and that's it. No other set of outcomes satisfies that the sum is at most 8 and the values differ by at most 1. Yes? All right. So, we took the intersection of two things. Well, what's our probability? We do a count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, there's 10. And divide by 36. And I forgot to put a question mark here. There we go. You might, now I understand, like, what? Wait, what was the question? No. And that becomes 5/18. All right. Okay, let's try another one. A random number is chosen from 1 to 1,000. Okay, so we pick a number. 611. All right, there's an example. Now the question, what is the probability that it is divisible by either 3 or by 5? Well, 611 is not divisible by 3 or 5, but that's just one number. So we have to figure out what's the probability that's divisible by either 3 or by 5. How can we approach this? Well, we have the word or. So or is very indicative of union. So let's let's come up with clever names. Let's let t equal divisible by 3, since 3 just starts with t. I don't know if this is a great choice I'm making here. And let's let f equal divisible by 5. So we're trying to find the probability of t union f. Right, because it's an or. And we have a nifty formula. It's the probability of t plus the probability of f plus the probability of t intersect f. Oh, sorry, not plus, minus. Minus. Okay, so we just have to figure out these three quantities. If we figure out these three probabilities, we have this one. So which one should we tackle first? Let's do the first one. How many numbers from 1 to 1,000 are divisible by 3? So at first, it might sound like a hard question, right? So what can we do? We can start listing them. 3, 6, 9. And then we realize we're going to be here a while. And I know we have time left in class, but not that much. So we say, okay, ... and the last number divisible by 3 less than 1,000 is 999. That's divisible by 3. So that's the possible outcomes, the event that you're divisible by 3. Now here's a fun little trick. We call it in the business divide by 3. And the way it works is you divide by 3. So if you divide by 3, you can say, well, this matches up really nicely to 1, 2, 3, all the way up to, what's 999 divided by 3? 333. So you might say, how many times does that happen? But how many times does this happen? Well, 333. So it helps to say, the probability that you're divisible by 3, well, there's 333 numbers out of 1,000 that are divisible by 3. Now, let's try the probability that you're divisible by 5. We'll do the same thing. We start listing the multiples of 5. 5, 10, 15. What's the largest number divisible by 5, but less than or equal to 1,000? 1,000. And I say, well, how many numbers are there? Again, if we divide, that's 1, 2, 3, all the way up to 200. So what's the probability that you're divisible by 5? 200 over 1,000. And by the way, this probably makes sense. Like 333 over 1,000 is like 1/3. 200 over 1,000 is 1/5. And you're like, okay, that makes sense. Divisible by 3, that should happen 1/3 of the time. Divisible by 5, that'll happen 1/5 of the time. All right, but what about the probability that you're divisible by 3 and by 5? So how do you find the numbers that are divisible by 3 and 5? If you're divisible by 3 and you're divisible by 5, what must divide you? 15. So if you're divisible by 3 and by 5, you're divisible by what you would call the least common multiple. Now in this case, because 3 and 5 are relatively prime, it's not too hard to find the least common multiple. It's just 3 times 5 is 15. And we say, cool. So we start writing the numbers down. So we're going to have 15, 30, 45, and ... And where do we stop? Well, 995 is not divisible by 3. But good guess. That's what I would have guessed. So it's 990. So 990 is divisible by 3, and it's divisible by 5. So that's the largest number. Okay, so again, how many are there? Well, here, divide by 15. 1, 2, 3. And, oh my goodness. 990 divided by 15 is a number. I think it's 66. We'll say it's 66. Is it 66? Now I don't know. Okay. All right. That's why we invented calculators, right? 990 divided by 15. It is 66. Okay, good. All right. So we add, and now we subtract 66 over 1,000. And what do we get? Well, we don't need to do this in our heads. We can take 333 plus 200, subtract 66, equals 467 over 1,000. Or, in terms of decimal, 0.467. So, turns out slightly less than 50%. But not bad. Okay. Any questions? All right. So, 5 students all have a birthday in September. What is the probability that 2 of them have the birthday on the same day? So they already have the birthday on the same month. What's the probability that they have it on the same day? Now, what makes this a complicated question? Or is it complicated? Maybe it's not complicated. How is it possible for 2 people to have a birthday on the same day? Well, there's lots of ways. But what makes this interesting is that, what if you have 3 people who have the birthday on the same day? Do you count that event? Is that a yes? For we should include that in our count? What if all 5 of them have the birthday on the same day? Or maybe 2 have a birthday on the same day, another 2 have a birthday on a different day, and yet another person has a birthday on the last day. All of those are situations where 2 of them have a birthday on the same day. So thinking about all the possible ways that people might share a birthday leads to many possible outcomes. So how do we approach this problem? Well, let's think about the complement. What's the complement saying? So if we want us to ask what's the probability that 2 of them have the birthday on the same day, think about what the complement of that event is. So the event that we're interested in is at least 2 people have a birthday on the same day. What's the complement of that event? What would be the opposite of that? But let's be a little bit specific. So the suggestion is not having a birthday on the same day. But I want to be a little bit more specific. If we compare the birthdays of all 5 people, what must be true? Well, we know they all have birthdays in September, but again, if we compare their birth dates and we're in the complement, what must be true? So the complement is all 5 people have distinct birthdays. That's the complement. Because if all 5 people have distinct birthdays, we don't count it. And if that's not true, then at least 2 of them share a birthday. So the question becomes, can we count this? I claim we can. Let's first think about how many days are there in September. I know that was a few months ago. There's the rhyme, 30 days hath September, April, June, and November. So there are 30 days in September. So we have 30 days in September. By the way, before we go too far, what do you think? Is this going to be a very unlikely event that 2 of them have the same birthday in common? Or moderately likely or extremely likely? We don't know, right? We'll find out. Okay, so there's 30 days in September. Now, we can think of our sample space as, day of the first person, day of the second person, day of the third person, there's day of the fourth person, and day of the 5th person. Quick question. How big is our sample space? How many options do we have for the first person's day? Now this is again just our sample space. I'm not taking into account anything. 30. The second person? 30. Third person? 30. 30. 30. So the size of our sample space is 30 to the 5th. 30 times 30 times 30 times 30 times 30. I hope that there was enough 30s in there. Now, what's the size? So this is the complement. We'll call this E complement. The complement, or the size of our complement of our event. So, let's just assign days. They all have to be distinct. How many choices do we get for the first day to pick? 30. How many choices for the second day? 29, because I can't repeat a day. How many choices for the third day? 28. How many for the fourth day? 27. And for the last day? 26. So the probability of E complement, well, that's 30 times 29 times 28 times 27, 27 times 26 over 30 to the fifth. Well, that I'm not going to do in my head, but that's okay. We can just use technology. So 30 times 29 times 28 times 27 times 26, divide by 30 to the fifth equals 0.7037, and that'll be enough for us for right now. Now, that's the probability of the complement. So how do you find the probability of the original event? What do you do? If you have the probability of the complement, to get the probability of the original event, you take 1, subtract. So, if we take 1 minus 0.7037, so make this negative. Oh gosh, how do I get my answer? One of these days I'll learn how to work my calculator. Okay, well, we'll just do 1 minus 0.7037. And we get 0.2963. Almost a 30% chance. So if you have 5 people, even though there are 30 days, we're already at 30% chance that 2 of them actually land on the same day. Now that's probably higher than most people think. It's one of the things that we call the birthday paradox, which is you say, suppose I have a group of people. What's the likelihood that 2 of them share a birthday? And so you say, well, if I want to have 2 people share a birthday, I probably need to have a lot of people, maybe 100, maybe 200. But it turns out that by the time you hit 30 people, the odds that they share a birthday is above 50%, which is not what you would think. So there's a question that sort of gets to this. How many students all having a birthday in September do there need to be until the probability that 2 have the same birthday is greater than 50%? So we already saw that with 5 people, we are at 0.2963. Now that's not bigger than 50%, so we need more than that. So let's do the computation. Let's just sort of go up and see what happens. At 6 people, well, if we run through what we did, we are going to compute the complement, so it's going to be a 1 minus. And then downstairs we have 30 to the 6. Then upstairs we'll have 30 times 29 times 28 times 27 times 26 times 25. Okay, now we patiently punch this into our wonderful devices here, and we'll see what that number turns out to be. 1 minus 30 times 29 times 20 times 28 times 27 times 26 times 25. Divide by 30 to the 6. We've jumped from 30%, now we're at 41%. Even one more person, our probability jumped up by 10% that we share a birthday. Not up to 50% yet, though. N equals 7. 1 minus, 30 times 29 times 28 times 27 times 26 times 25 times 24, all over 30 to the 7. Right? So I'm just doing what we did up here. you're just adding another number. And, okay, we can probably just modify our last computation times 24. Divide by 30 to the 7, and we're at 0.5308. So the answer, 7 people. So if you have 7 people, all of whose birthday is in the same month, then you have a better than 50% chance that 2 of them have their birthday on the same day. Okay. All right, how are we doing on time? I think we can do the last one. The last one is fairly straightforward. So, a survey is conducted of 1,000 undergraduates. And the survey found that 750 students owned laptops, 450 students owned cars, 350 students owned both a laptop and a car. Now the question, what's the empirical probability that a typical student, and then you have owns either a car or a laptop, owns neither a car nor a laptop? Now, what's going on here? Well, this empirical probability says, look, I'll ask a lot of people. It's like I'm running this experiment many times, and we have reason to believe that the people that we ask are reflective and they're typical, so that if we kept going, we'd see roughly the same kind of outcomes. So it's the experimental outcomes. So we say, look, this is really a question about sets. So we can draw a Venn diagram. Now, we have our universe, and in our universe, there are 2 categories. There's laptops, and there's cars. Now, what are things that we know? This 1,000, what does that tell us? In terms of our Venn diagram. So 1,000, that's the total number of people that were surveyed. So the size of the universe is 1,000. 750 students own laptops. Well, that says the size of the set of laptops is 750. 450 students own cars. So the size of the people in the set of who are car owners is 450. And 350 own both a laptop and a car. How do we denote that? That's intersection. Now from this you can quickly derive some numbers. So we say, I see the intersection is 350, so that's how many people are in both. The total number inside of cars is 450. Here is 350. So what must be in this part? 100. Total number of laptops is 750. There's 350 here. How many are in this piece? 400. If I add these up, 100 plus 400 is 500, plus 350 is 850, meaning there's 150 here. So, question. You ask a student, what's the probability that a typical student has either a car or a laptop? What are you after in that question? Either or means you're after this part. Well, you just do a count. You add 400 plus 100 plus 350, that's 850, out of how many people were surveyed? The size of the universe, 1,000. Or it's 85%, 0.85. How many people own neither a car or a laptop? What's that? It's the stuff out here. And what's that number turn out to be? 15%. Yeah, 150 over 1,000. 15%. All right. Thank you. That's it for today.